You know how Netflix just knows what show you're going to want to watch next? Or how a weather app can tell you tomorrow's temperature? Well, a lot of that magic comes down to a powerful machine learning technique called regression. And today, we're going to pull back the curtain and see exactly how it works. It really all boils down to this one big question, right? How can we take all the stuff we already know, all the data from the past, and use it to make a really good guess about what's coming next? That's the exact puzzle that regression is built to solve. So, what is regression really? Well, at its core, it's all about predicting a number. It could be the price of a house, the temperature outside, or, like we're about to see, how many ice creams you might sell on a hot day. The key thing to remember is that it learns from data where we already know the right answers. So here's the plan. We're going to walk through what regression is, train our very first model, and then figure out if it's any good. We'll even grade it with some key metrics, and then zoom out to see how this all fits into the bigger machine learning loop. Let's jump in. All right, let's do this. Time to train our first model. This is where we go from just a pile of data to something that can actually make predictions. We're going to use a super simple classic example: ice cream sales. What you're looking at here is data from 12 different days. We've got the temperature for each day and how many ice creams we sold. I mean, it makes sense that hotter days mean more sales, but let's see what the data has to say. Now, the very first thing we have to do might seem a little weird. We have to hide some of our data. We split it into two piles. One part is for teaching the model. That's our training set. The other part we'll save for later to test it. It's basically like giving it a pop quiz to make sure it actually learns something. Okay, so here are the 6 data points we'll actually use to teach our model. This is the only information it gets to see. It's going to look at these numbers and try to find the relationship between how hot it is and how much ice cream people buy. It has no clue the other 6 data points even exist, yet. So what happens now? Well, we feed this data to a simple algorithm called linear regression. Its job is to look at these dots on a graph and draw the one single straight line that gets as close as possible to all of them. This line is everything, because once we have it, we can turn it into a simple math function, our own little prediction machine. And there it is. The algorithm crunched the numbers and came up with a rule. It's a simple one. To predict ice cream sales, just take the temperature and subtract 50. That's it. That's our model. So, we have a model. Awesome. But is it any good? How do we find out? Well, it's time to bring back that data we hid earlier. It's quiz time. Here's our test data. We've got the temperature and the actual number of sales for these 6 days. And now we're going to ask our model, using only the temperature, to fill in that blank column with its best guess. And here are the results. The third column shows what our model predicted. And you know what? It's not bad. The predictions are definitely in the ballpark of the actual sales. They're not perfect, but that's okay. The goal isn't perfection, it's to be useful. This is where you can really see what's happening. All of our model's predictions land perfectly on that straight line it drew. But the real world, it's a bit messier. The actual sales numbers are scattered around that line. That little gap between a real data point and the line, that's our error. That's how wrong the model was on that day. Just saying our model is pretty close isn't very scientific, is it? To really know how well it did and to compare it to other models, we need a way to grade it. We need a report card with some actual scores. So first up is mean absolute error, or MAE. This one's the most straightforward. We just look at the error for each prediction, find the average of all those errors, and that's it. It just asks a simple question: on average, how far off were we? For our model, the MAE is 2.33. So what does that actually mean? It means that, on average, our prediction was off by about 2.33 ice creams. Pretty easy to understand, right? But what if being really wrong is way worse than being a little wrong? That's where mean squared error, or MSE, comes into play. By squaring each error before it finds the average, it punishes the big mistakes a lot more. So if you're off by 4, that gets penalized way more than being off by 2 twice. Our model gets an MSE score of 6. But 6 what? 6 squared ice creams? It's kind of weird, right? The units get all funky, which makes this number really hard to interpret on its own. So to fix that whole squared ice creams problem, we use root mean squared error, or RMSE. And it's exactly what it sounds like. We just take the square root of the MSE. This magically brings our measurement back to units we can actually understand: ice creams. And there we go. Our RMSE is 2.45 ice creams. Now that's a number that makes sense. You might notice it's a little higher than our MAE was, and that's because it's still feeling the effects of punishing those bigger errors more harshly. Okay, last metric, and this one's a bit different. It's called R-squared. Instead of measuring error, it asks, how much of the story does our model actually explain? In our case, how much of the change in ice cream sales can be explained just by the change in temperature? The score is between 0 and 1, and the closer to 1, the better. And our score is 0.95. Wow, that is incredibly high. It means that 95% of the reasons sales went up or down can be explained by the temperature. So our very simple model is actually doing a fantastic job. So we built a model, we tested it, we graded it, and it's pretty good. But in the real world, this is where the work really begins. Because this whole thing, it's a loop. A data scientist wouldn't stop here. They'd go back and try to beat that 0.95 score. Maybe they'd add more data, like whether it was a weekend. Maybe they'd try a totally different, more complex algorithm. They'll keep tweaking and experimenting, running this loop over and over, always checking those scores to see if they're getting better. So you see, building a machine learning model isn't this one and done thing. It's a cycle of building, testing, learning, and refining. It's part science, and it's also part art. Which kind of leaves you with a big question, doesn't it? How many loops does it really take to get from a good model to a great one?